Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
In this problem, we're asked to use Ampere's law to figure out how large the magnetic field is going to be within a wire at some particular distance from the center of the wire up to the surface. If we have a uniform current distribution across the cross-section of that wire. So we know that we have some wire, and I'm going to draw it rather thick for illustrative purposes. Of course, when we just look at wires, they usually look pretty thin. But we'll draw this cross-sectional area of this wire here. So overall, a current I naught is going to be going throughout this entire wire, but that's distributed all completely throughout this wire. So if I wanted to know how much current is going through, let's say, not the entire wire, right, around all here, but say instead I wanted to know how much current was only going through this much, right, of wire, then I would need to know something about the current density, which is what we do know that. So say we have this little circle of little radius r here, right? Imagine we wanted to know how much of the entire current I naught is going to be traveling through that bit. Well, I would need to know the cross-sectional area of my little green circle here, and that's going to be pi r squared, of course. And then I would need to know the current density. So how much current is will be encapsulated by each of these cross-sectional areas when I draw them. So I've given that the current per cross-sectional area is I naught divided by the entire cross-sectional area of the entire wire. So I take this, multiply it by the cross-section I care about, and I get how much current is going through just that little square, right? So you'll see that if I did want to use the circle of all of this, well, what would I plug in for my radius? Big R. Well, if I plug that in there, I get that the current through all of the wire, right, is I naught over 2 pi big R squared multiplied by pi big R squared. Oh, sorry. The 2 pi. I wrote by accident. Let me erase that. That 2 should not be there. That's an accident there. Okay, so now that I have this, I see that these cancel. And of course, that the current going through the entire wire is just I naught. So that's just an illustration of purposes. So that if I want any of the wire enclosed by any particular circle made of little r, then I just need to take the current density I naught divided by pi big R squared and multiply it by the cross-sectional area of the little circle that I care to know about how much current is in that. And so knowing how much current is enclosed in the circle we draw is going to be important, right, for Ampere's law. So if I use Ampere's law, it says that if I sum up all of the components of my magnetic field that are perpendicular to little tiny paths delta L that I travel around some Amperian loop, that's going to be equal to mu naught times the enclosed current that I have. So let's draw, let's start fresh and draw an Amperian loop. We'll keep using the green of radius r, right? So even inside a wire, magnetic fields still circulate in circles. So for my sum of the multiplication of all the parallel components to my little small distances, well, my magnetic field is going to be parallel to my small distances delta L everywhere. And we're going to see something similar that we've seen before, that this summation up here ends up being just the magnitude of magnetic field times the circumference, the whole length that I've gone around of my Amperian loop of small radius r. Now, if I draw draw this loop of small radius r, like we just discussed, the amount of current that I have enclosed in that is I naught divided by pi big R squared multiplied by how big the surface cross-sectional area of my Amperian loop is. So now I think I've pretty much arrived at my answer. I just need to do some simplifications. So we see that one of these pi's is going to cancel, and one of the r's is going to cancel here. Do we have anything else? I don't think so. So we rearrange this, and so we see that the magnetic field inside of a wire that has a uniform current density distributed through it is going to be equal to mu naught times the total current through the entire wire multiplied by how far out we are from the center of the wire up to the surface, divided by 2 pi times r squared, big R squared, sorry. And that is what we were asked to prove is the case.